Oxidation-reduction reactions are another category of reactions. Here what we've got is electrons being transferred from one reactant to another. Oxidation reduction is a lot of syllables, and so it's often abbreviated as redox reactions. Many redox reactions involve something reacting with oxygen. Here's some examples. This is iron rusting, combustion of octane, and here's hydrogen and oxygen combining to form water. So all of these, we have oxygen as one of the reactants. These are all redox reactions. See, an oxidation reacting with oxygen, right? That's not a coincidence. That's where the word oxidation comes from. So here we have a balloon filled with hydrogen and oxygen. Very fun. You give that a little spark and it goes kablooey. A balloon that big would give off enough of a shockwave that it would make the ceiling tiles in this room bump up. It's a lot. Very vigorous reaction there. We can also have a redox reaction without oxygen. So it's not a combustion reaction. Here's an example, a metal and a nonmetal reacting together. So here we have sodium metal and here we have chlorine gas. Both of those are not good for you to ingest. You combine those two together and they form sodium chloride, which is necessary for life. Not too much, but you need some. What happens here is that the sodium becomes a sodium cation. It does that by losing an electron. And the chlorine atoms become chloride ions. They do that by accepting an electron. So an electron has been transferred from sodium to chlorine. So we could look at these. Here we have sodium reacting with oxygen to form an oxide. So that could be considered a combustion reaction. Here we have a metal reacting with a nonmetal, forming an ionic compound. So if we look at these products, those are ionic compounds, right? A metal, nonmetal, we learned that those were ionic, and we learned how to predict the charges. These are uncharged elements. So we've got the element sodium, the element oxygen, and now we've got ions. And this is a great illustration of why we don't include ion charges in the chemical formulas, because it gets a little messy, right? But the charges are there just to point out that this is now sodium ion and this is oxide ion. And a similar thing happens when it reacts with chlorine. It's sodium ions and chloride ions. Yeah?
But those aren't both redox reactions, right?
They are both redox reactions.
I thought you had to have oxygen.
Many have oxygen.
Oh.
Many of them have oxygen, but now I'm showing you some that do not.
Okay. So how would we, I mean, like I could tell, okay, when it has oxygen with redox, but
How do you identify? You have to look and see where electrons transferred. So how did this, I lost my pointer. How does the sodium atom become a sodium ion? It lost an electron. How does the chlorine become a chloride anion? Gained an electron. So an electron was transferred. One of them was oxidized, one of them was reduced. The term oxidation came from originally something combining with oxygen, but when we came to understand more what was actually occurring, now we know that it's not just oxygen, it's actually the electron transfer. When you have things combining with oxygen, you also have electron transfer. Make sure I didn't skip anything. So to go from an element into an ion, the atom must either gain or lose electrons. And electrons are something that, like those hydrogen ions, are not just out there by themselves. If one atom loses an electron, another one has to take them. And if you want an electron, you have to get it from somebody else. So there's no homeless shelter for electrons. There's no bank where you can go check out electrons, no library. It's just passed from one to the other. So oxidation-reduction reaction, something's being oxidized, something's being reduced. Something's losing electrons, something's gaining electrons. So oxidation is when something loses electrons. Reduction is when something gains electrons. And again, that's that two things, and you got to remember how they go together. So the mnemonic oil rig can help us remember that. Stands for oxidation is loss of electrons. Reduction is gain of electrons. So when we look at this reaction between sodium and chlorine, the sodium goes from an atom to an ion, and it does so by losing an electron. Oxidation is loss of electrons. The sodium is oxidized. Chlorine becomes an ion by gaining electrons. Reduction is gain of electrons. So one thing's being oxidized and the other thing's being reduced. So we can see that more clearly with ions, but we can also have an incomplete transfer of electrons between nonmetals, and it's still considered an oxidation-reduction reaction. So if we look at the reaction between hydrogen and chlorine, hydrogen is a molecule with two neutral atoms. Chlorine is a molecule with two neutral atoms. When they react, they form two molecules of HCl. So here we've got the hydrogen molecule and the chlorine molecule. And because these two atoms are identical, they're going to share their electrons equally. But when we have hydrogen and chlorine together, the chlorine hogs the electrons, pulls them away from the hydrogen. Those electrons are not being shared equally anymore. It's not a complete transfer of an electron, but there's been a shift of electron density. So the chlorine now has gained electron density, and the hydrogen has lost electron density. So the hydrogen is oxidized and the chlorine is reduced. So that can be harder to see, right? Any questions so far? So looking at two nonmetals reacting, it's harder to tell if you have a redox reaction because you can't look at ion formation. You can't just say, oh, well, that's reacting with oxygen, it's redox. Things like hydrogen and chlorine reacting together. So we came up with something called oxidation states, sometimes called oxidation numbers. And this is an artificial thing that we do looking at the molecules to identify where electron density moved before and after. So oxidation states are not ion charges. They're imaginary charges that we assign based on a set of rules. Ion charges are real, they can be measured. Oxidation states are completely made up. What kind of makes this confusing and yet makes it easier too is that the oxidation state is often the same as the ion charge. So let's look at these rules. And anytime you spell everything out, it makes it look actually a lot more complicated than it is. So you go in order of priority through these rules. Free elements have an oxidation state of 0. Monatomic ions, so this has a charge, its oxidation state equals its charge. If you have things in a compound, like here you have two ions in a compound, overall this has a 0 charge, and so the oxidation states have to add up to 0. So far, this is acting exactly like ion charges. Some of the oxidation states for neutral molecule has to be 0. If you have a polyatomic ion, such as nitrate ion, this thing has a charge of -1. All of the charges, the oxidation states, have to add up to -1. Metals always have positive oxidation states. Group 1 metals are always +1. That's the same as their ion charge, right? Group 2 metals are always +2 oxidation state. That's the same as their ion charge. So far, this is all pretty much the same as ion charges. It's the nonmetals. And this is where we need oxidation states, because in molecular compounds, the nonmetals don't have charges, and yet there can be that shift of electron density. So we use the oxidation state. It's like a fake ionic charge to help us decide, well, who is hogging the electrons? So this is the table that we need to remember. And so this is how I remember it. So if I take that F and just fill in the end of it, that's Fa, right? You like? No. I would have left at the F then. Pho. You know what pho is?
It's like pudding.
It's noodles.
Oh.
Is it Vietnamese? Vietnamese noodles? Yeah, really yummy stuff, right? Pho. And what's funny is in Fresno, there's actually a restaurant named Pho 76. Anyway, Pho 765. Can you remember that? So it's really not a P, it's an F. And it says the F sound, right? So Pho, P-H-O, F-H-O 765. That's this order, F-H-O 765. The oxidation states are the charges it would have if it was an ion. If fluorine becomes an ion, it has a -1 charge. If hydrogen becomes an ion, it has a +1 charge. Oxygen would have -2. The rest of the things in group 7, -1, group 6, -2, group 5, -3. So what this is, it's a list of who gets their choice. Because when we've got two things like carbon and oxygen, how do we decide which one has to be positive and which one has to be negative? You go through the list. Pho, F, H, O. Okay, oxygen is highest on the list of things that are in carbon dioxide. Oxygen gets to choose its oxidation state. Oxygen is going to choose -2 because that's what it would do if it was an ion. The carbon then has to make up the difference. So carbon dioxide, a neutral molecule. So the oxidation states have to add up to 0. There are 2 oxygens, they're each -2, so the carbon has to be +4. So we're just going to go through this list, and whoever is first on the list gets to choose what they want, and other people have to make up the difference. You can have fractional oxidation states. We're not going to see them very often, but it's possible. For oxidation states, we write the sign before the number. We write it after the number for ionic charges. I'm not going to try to trick you on that. Let's practice. So here we have the element chromium. What's its oxidation state? What's its charge? You don't even have to look at the periodic table. Is there a charge on it there? No. It's an atom. So its oxidation state is the same as its charge, it's 0. All elements have 0 oxidation state. What if it becomes a Cr3+ ion? The oxidation state is going to be equal to its charge. So the oxidation state is +3. Here we have carbon tetrachloride. We have 2 nonmetals. We can't look at charges. You can only do charges if you have an actual ion, or if you have something like this where you have an ionic compound and you could look at individual ions. So here we have carbon and we have chlorine. So then we say Fe765, and we go down the list. Do we have any fluorine? Nope. Do we have any hydrogen? Nope. Oxygen? Nope. Group 7 elements? What group is chlorine in? Group 7. That's not a very good Cl. If chlorine was an ion, what would its charge be? It would like to be chloride, right? It would like the charge of -1, so its oxidation state is going to be -1. So in carbon tetrachloride, we have 2 elements. We have carbon and we have chlorine. The chlorines are going to have -1 oxidation state. Each of them. There's 1 carbon and there's 4 chlorines. If all 4 chlorines are -1, what does the oxidation state on the carbon have to be? +4. It's just like doing ion charges. If we were looking at SnCl4, tin, and we were trying to figure out what the charge on the tin was, we would do exactly the same process. So here we're pretending, sort of. We're using oxidation states as pretend ion charges. So there we've got carbon +4 and chlorine -1. Here we have an ionic compound. We can look at the charges on the ions. What's the charge? Let's do the bromine first. What's the charge on the bromine? -1? Because it's in group 7? What's the charge on strontium ion? What group is it in? It's in group 2? So +2? So the strontium is +2. SO3. This is not sulfite ion. This is sulfur trioxide. There's no charge on this. It's a neutral molecule. We have 2 nonmetals, so we're going to do Fe764. Fe765. No fluorine, no hydrogen. Oh, we've got oxygen. What would oxygen like to be? -2. So, in that compound, we've got sulfur and we've got oxygen. Oxygen gets to choose, gets to be -2. Sulfur then has to be whatever it needs to make up the difference, because all those oxidation states have to add up to the overall charge, which is 0. So what's the sulfur? +6. Now, have we ever seen a sulfide ion with a +6 charge? No. And this doesn't have a +6 charge, but it has a +6 made up oxidation state. Here we've got NO3-. This is nitrate ion. So we've got 2 elements. We've got nitrogen and we've got oxygen. And we go through Fe765, fluorine, nope, hydrogen, nope, oxygen. Oxygen gets what it wants. It wants to be -2. Now this one's not quite as easy as the SO3. So I've got a nitrogen and I've got 3 oxygens. 3 oxygens, each of them is -2. And overall this has to add up to -1. So this is a total here of -6. If I make the nitrogen +6, then it's going to have a 0 charge, right? So the nitrogen needs to be +5, because 5 and -6 is -1. Any questions? This is going to take some practice. Yeah.
So that
Yes. The sum of the oxidation states for all the atoms in a polyatomic ion will add up to the charge on the ion. If you have a neutral molecule, the sum of the oxidation states will be 0, which is the charge on the neutral molecule. It's 0. We are going to finish this. We're almost there. So, how do we identify redox reactions? What we're looking for is something being oxidized and something being reduced. We got, so we talked about that in terms of a loss or a gain of electrons. We can also think of it as a change in oxidation state. Oxidation is an increase in the oxidation state. Reduction is a decrease, a reduction in the oxidation state. Okay? So oxidation, the oxidation state gets bigger, more positive. Reduction, the oxidation state gets smaller, more negative. So we can look here at carbon and sulfur reacting to form carbon disulfide. And here we have two elements. They're both starting out with oxidation states of 0. In this compound, we go Fe765, and we find that sulfur gets first choice. Sulfur wants to be -2. There's 2 of those, and so carbon must be +4, so that all of those add up to the overall charge on that, which is 0. Then we can look and see that carbon went from 0 to +4. Its oxidation state went up. It was oxidized. Sulfur went from 0 to -2. It went down. A reduction. So we have something being oxidized, something being reduced. This is a redox reaction. Any questions? Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. When there are charges, just use the charges, because they're the same as the oxidation states. What's the charge on this tin? 0. That one looks messy. Let's skip that one. Here we have SNO2. Is that an ionic compound? Yeah. It's a metal and a nonmetal. So we could look at the individual ions. We've got tin and we've got oxide, and we know that oxide is -2. And so from the charges, we can figure out that the charge on the tin there is +4. For ions, the oxidation state is the same as the charge. So the tin is +4, the oxygen's -2. Then we get into these, and these are just all nonmetals, and so now we can't really look at charges. We do have to look at oxidation states. Fe765. So this would be -1, +1, oops, -2. -1, -2, -3. Let's start with water at the end here. We've got hydrogen and oxygen. We go Fe765, fluorine, nope, hydrogen. Hydrogen wants to be +1, so he gets to choose. And then what does oxygen have to be to make it up? -2. Oh, well that's convenient because that's what oxygen wanted. And let's look at this one, NO2. Who gets first choice? Oxygen, Fe765. Nitrogen's down here in group 5. So oxygen gets to be -2. So the oxygen's -2. What's the oxidation state for the nitrogen? +4. The coefficient just means I have 4 of those. It has nothing to do with the oxidation states. Okay. So then we have to get back to this one. Who gets first choice? Fe765. Hydrogen, right? Hydrogen wants to be +1. Now I've got nitrogen and oxygen. How do I decide? I stick with the list. Oxygen gets next choice because it's after hydrogen. Hydrogen chooses, then oxygen chooses, and nitrogen has to do whatever is necessary. So the oxygen here is -2. Now this is one we might have to think about a little bit more. So we've got a hydrogen that's +1, and we've got 3 oxygens that are -2, and then we have 1 nitrogen, this is this question mark. And all of this has to add up to 0. +5, right? So here the nitrogen is +5. Now that I've identified the oxidation states, I can look and see whose oxidation state is changing. Is the tin changing? It's from 0 to +4. Yeah, that's different. 0 to +4, is that oxidation or reduction? Oxidation. So the oxidation is the tin. And then I'm looking at hydrogen is +1 and hydrogen's +1, nothing happened there. Nitrogen's +5 and over here it's +4. Well, that's different. Did the oxidation state go up or down? From 5 to 4. It went down. So it was reduced. So the reduction is the nitrogen. It's possible for more than one thing to be oxidized, more than one thing to be reduced. You just have to have a minimum of one of each. So let's check the oxygen here. Here we've got -2, and over here it's -2, and there it's -2, and there it's -2. The oxygen didn't do anything. Any questions?